In this lesson, we'll talk about factorization of polynomials. To factor means to rewrite the expression, in our case polynomial, as a product of simpler expressions, in our case polynomials of lower degrees. So, for example, this quadratic trinomial is factored into linear factors x minus 3 and x plus 7. Some polynomials can't be factored. For example, 2x plus 3, this is already linear polynomial, so it can't be broken down into lower ones. Also, the coefficients do not have common factors, so there's nothing we can do about this one. Such a polynomial is called prime. So prime polynomial can't be factored. Another example, sum of squares, x squared plus 1. Sum of squares is not factorable. And the following example, x squared plus x plus 1. You may want to check that one. Plug in to the calculator as a function y equals x squared plus x plus 1, and you will notice that the graph of this polynomial is a parabola that is above the x-axis, so it doesn't cross it. Therefore, this function doesn't have any roots, which means that the equation x squared plus x plus 1 equals 0 doesn't have any solutions. So this polynomial couldn't be factored into linear polynomials with integer coefficients, as otherwise we would have some solutions. Now, to factor a polynomial completely means to rewrite the polynomial as a product of prime polynomials. That means we factor until all factors are prime. We have several strategies to factor polynomials. The very first strategy is checking for common factors. So, for example, we'll look at all coefficients. If those coefficients have a common factor, we pull it out. For example, these numbers have common factor 4. But also, watch the leading coefficient. If it's negative, let's pull the negative out of the bracket as well, because the remaining polynomial in the main bracket should start with a positive number. Okay, as a matter of letters, we have powers of x here, and there, and there. We are choosing this common base, and we are choosing the lowest exponent. Since the exponent of x is 4, 3, and 1, the lowest is 1, therefore we can pull just 1x. The same is with y's, here, here, and there. Yes, the y is common, but the lowest exponent is again 1. So that's the greatest common factor that we can pull out of the main bracket. And what's in the main bracket? Basically, to find out those expressions, what we do, we divide the term by the common factor that we took out of the bracket. So negative 12x to the 4y when divided by negative 4xy is 3x cubed. Y is totally gone. Next, plus 16 divided by negative 4 is negative 4. X cubed divided by x is x squared. And y squared divided by y is y. Finally, negative 8 divided by negative 4 is plus 2. And then x is gone and y squared left over. Here we go. In the following example, we have actually two terms, two clusters connected by multiplication. This one and that one. What's common for those two terms? We can observe that the bracket repeats. So the bracket is the common factor that we're going to pull out of the main bracket. Let's do it. X minus 1, and what's remaining is 2x plus 3y. And it's factored. In the following example, again we have two terms, this one and that one. The common factor is the same bracket, 2x plus 1. It appears here and there. So let's pull it out. 2x plus 1. And what's left in the remaining bracket is this part, x plus 5, minus, we need to be careful because of this minus and incoming bracket. So we write minus and we write x minus 7 in a bracket. We're going to release this bracket in the next step. Okay, equals, let's copy to x plus 1, release the inner bracket, we'll get x plus 5 minus x and plus 7. Now we can notice that this x can be reduced with the negative x and we really end up with 12. So the overall answer equals, let's write the 12 in front, 12, and then bracket 2x plus 1 as a final answer. Here we have expression that is not really a polynomial, but we can still attempt to factor it. Let's take common factor for numerical coefficients with the negative sign. So it's negative 2. And then we use the base a to the lowest exponent. So out of negative 3, negative 5, and negative 4, negative 5 is the lowest. So we pull a to the negative 5 out of the bracket. Now, what remains in the main bracket? Well, the negative 2 is pulled out, so there is no number. But what about the letter? A to what exponent? Well, let's see. When we multiply back, negative 5 plus what number is negative 3? Well, the number must be 2. Negative 5 plus 2 is negative 3. So that's one way of obtaining this exponent 2. The other approach would be just divide a to the negative 3 divide by a to the negative 5. Remember, when we divide powers, we subtract exponents. So it's the same calculation as negative 3 minus negative 5, which is the same as negative 3 plus 5. Negative 3 plus 5 is 2. Okay, let's look at the second term. This time, since we pull the minus out, the remaining sign is also negative, and 6 divided by 2 is 3. However, a to negative 5 was already taken out, so there is no a left over. And finally, the last term, again, switch the sign, it will be positive. 14 divided by 2 is 7, and a to what exponent? Well, if we multiply back, negative 5 plus what is negative 4? Well, plus 1. So we don't really need to write this 1. It's just a single a. That's the end. The only thing that we can still do is to arrange this polynomial in decreasing order of exponents so it will look nicer. So negative 2a to the negative 5, and then in a bracket we have a squared plus 7a minus 3. We should ask ourselves, is this quadratic trinomial factorable or not? However, since the last number is negative 3 and the middle number is 7, well, we don't have two integers that will multiply to negative 3 and add up to 7. So this is a prime polynomial. We can't factor it anymore, so that's the end. The next strategy, just after factoring the common factor, is factoring by grouping. Sometimes a polynomial doesn't have a common factor for all terms. We may not be able to find a common factor for all terms, but if we look just at the first two terms and last two terms, we may have common factor within these two groups. For example, here the common factor for the first two terms is 2y. So let's pull it out, 2y. What's left in the bracket is 3x from the first term and minus 2 from the last term. Let's look at the second pair of terms. Again, we have a common factor which is 5. Let's pull it out. And what's inside is again 3x minus 2. That's great, because as soon as we have exactly the same bracket, we can pull it out of the whole polynomial. 3x minus 2, and what remains is 2y plus 5. So, factoring by grouping helped us to factor this whole polynomial into two linear polynomials. Very powerful strategy. Okay, another example. Again, let's try to group 2 by 2 and see what will happen. From the first two terms, let's take xy, that's a common factor. What's left is 5 minus x. And from the last two groups, we can pull 2, but with a negative sign, because we predict that we would like to keep the bracket starting with positive 5. So let's pull the negative out. Okay, negative 2 times 5 is negative 10, and negative 2 times negative x is positive 2x. Great, so again we have exactly the same bracket. We can pull it out of everything. So the remaining bracket is xy minus 2, and the polynomial is factored. The next strategy is to factor trinomials with leading coefficient 1 by using guessing method. So the idea is to rewrite this quadratic trinomial in a form x plus certain number p times x plus certain number q. What do we know about those p and q numbers? So yes, we guess those p and q numbers in such a way that after multiplying we'll get back our original polynomial, but let's observe how can we help ourselves to find out those numbers. First of all, if we FOIL back those factors, p times q will give us the free term c. And the middle term, that includes only one x, comes from multiplying the inner terms and the outer terms. Since the inner product results in px and the outer product results in qx, when we add them, the coefficient by the x is p plus q. So p plus q really gives us the middle coefficient b. Therefore, we are looking for two numbers that will multiply to c and that will add to b. So our guessing is really educated guessing. We'll also observe how to pull the information about the signs, the middle sign and the last sign. Let's see the following examples. I'm sure you won't have problem to factor these. However, let's observe the process. Let's prepare two brackets. We definitely have to have x and x over there. And since the product is positive 6, we know that the two numbers that we are looking for are of the same signs. We also know what type of signs should we use, because the sum is also positive. Therefore, the two numbers will be both positive. Okay, now product 6, sum 5. Well, 3 and 2 should work. So we place 3 and 2. Okay, the next question is very similar except for this middle sign is negative. So again, let's prepare two brackets, x and x. Product is positive, so the two signs of our future numbers are exactly the same. But what kind of signs? Well, negative signs. So two negatives. If the last term is positive, the sign of the middle term decides what signs will we take in those brackets. And again, the product is 6 and the sum is 5. So 3 and 2 works as well. Okay, let's check the other two examples. This time, the product is negative in both examples. So let's observe what will happen. The first x and x is the same. Since the product is negative, we need to use different signs. So let's place plus and minus. The same will be here. Product negative, so we place plus and minus. However, when we have our numbers with two different signs, when we add them, it's really like taking the difference between their absolute values. So we are thinking about two numbers that will multiply to 6 and that will actually differ by the middle coefficient, by 1 in this case. So two numbers that multiply to 6 and differ by 1 are 3 and 2 as well. But the middle term is more on positive side. Therefore, our larger number must take this middle sign. It will be positive. So we place 3 here and 2 over there. In the last example, though, the middle sign is negative. Therefore, the larger number takes the middle sign. It will be placed with the minus and the 2 with the plus. Okay, let's summarize this information. Since I didn't want to write too much, I try to put all the main information that we talk about when we solve these 4 examples in the following table. This could be quite a bit of shortcut, so if you prefer to write in words all this info, please go ahead and do it. Generally, for a better communication, let's assume that the absolute value of p is larger or equal than the absolute value of q. So basically we are referring to the larger number or smaller number, regardless of the sign. As you see in this table, we have 4 cases. The top 2 cases refer to the top 2 examples, and the bottom 2 cases to the bottom 2 examples. Also, the first sign in the table refers to the middle sign, and the second sign to the last sign. If we have the last sign positive, then we know that the product is positive, therefore the two numbers are of the same sign. They are either both positive if the middle sign is positive, or both negative if the middle sign is negative. And the coefficient b comes from summarizing these two numbers that we are looking for. In the last two cases though, if the product is negative, then the two numbers that we're looking for are of different signs. And if the middle term is positive, it tells us that the number with larger absolute value is positive and the other one is negative. In the other case, if the middle sign is negative, it tells us that the larger number comes with the negative sign, with this middle sign, and the smaller number is positive. To obtain the middle coefficient b, we're really finding the difference between the absolute value of numbers that we're looking for. So in this case, it will be the larger absolute value minus the smaller absolute value. And in that case, when the middle coefficient is negative, to obtain b negative, we go the other way around, starting with the smaller absolute value and minus the larger absolute value. Let's try those examples. Factor completely. Remember, anytime we try to factor, always look for the common factor first. Also, it's a good idea to keep in mind that we should arrange the polynomial in decreasing order of exponents, as well as pull the negative out of the bracket to start with a positive term. So, in the first case, what is our common factor? Well, it's 3 for sure, and there's no x and no a, so just 3. 3, and then in the bracket we have x squared plus 5xa and minus 24a squared. Great, but then we have a trinomial that could possibly be factored. Let's see if we can factor it. So keep the 3, prepare two brackets. The first term will be x for sure, here and there. The last term must include a, but it could have some coefficients in front of a. So again, the product is negative 24, so the two signs are opposite, 1 plus, 1 minus. And then product 24 difference, because of this minus, we're looking for difference to be 5. Well, 3 and 8 works. 3 times 8 is 24, and they differ by 5. The larger number takes the middle sign, so 8 goes with plus. So we place 8 here and 3 over there, and we're done. Okay, let's try the next example. Here, first let's notice that this polynomial is not written in decreasing order of exponents. Okay, we may want to rewrite this, and in the meantime, we could pull the negative 2 as a common factor. So, if I take negative 2 out of the bracket, and then start writing my terms from the highest exponent, that will be p squared. Next term is this one. When we take negative 2, what's left is plus 10p. Finally, the last term, since negative 2 is taken out, the sign will be reversed, so it's negative, and 42 divided by 2 is 24. Okay, and now we can look at this quadratic trinomial, try to factor it into two brackets, two linear polynomials. So, p and p for sure, and then we are looking for two numbers that will multiply to 24 and differ by 10. So it must be 12 and 2. 12 as a larger number takes the middle sign, so it's plus 12 and minus 2. Okay, that looks good. The following example has higher powers, but since the first term and the last term has an even power, and the middle term is the product of those powers, we can still factor the same way as before. Prepare two brackets, take square root of x to the 4, which is x squared, in both brackets for the first term, and the last term must involve y cube, because y cube squared is y to the 6. So it must be y cube for sure, with some coefficient in front of it. How to get this coefficient? By using the same rules as before. The product is 42, the sum is 13. So two numbers that will multiply to 42 and add up to 13, that will be 6 and 7. So it's plus 6 and plus 7. Plus because both of these signs are positive. So the expression is factored. The last example, let's search for common factor. Maybe it's a little bit unusual, but if we put the bracket around x minus 3, then we can notice that this bracket x minus 3 is repeating itself in every single term. So yes, that's a common factor, we can pull it out. And in the remaining bracket we have x squared minus 2x plus invisible 1. So x squared minus 2x plus 1. However, you probably recognize that this trinomial is actually a perfect square. It is a perfect square of x minus 1. So that's our final factored form. The next type of quadratic trinomials that we need to be able to factor are the trinomials with leading coefficient different than 1. So those are the hardest to factor just because there's so many possibilities. We're not only looking for numbers p and q, but also the coefficients by x. Let's call them m and n. So the last term of our trinomials, the c term, comes from the product of p and q that we are looking for. That's not a problem. The first term comes from the product of the leading coefficients in our brackets m and n. However, our main struggle will be to obtain the middle coefficient b. This middle coefficient b comes from multiplying the inner terms and the outer terms and adding them up. So if we multiply the inner terms, we obtain np x. When we multiply the outer terms, we obtain mq x, and then when we add these two terms, the coefficient comes from adding mq and np. So that's our b coefficient. Depending how complex are the outside coefficients a and c, that's how difficult the question may be. Because the more complex the a is, the more choices is for m and n. Similarly, the more complex is c, the more choices we have for p and q. So to help us factor this type of trinomials, we can use two methods. One of them is similar as in the previous case. It's basically a guessing method. We need to guess p and q and m and n. But if we have too many choices and we can't really guess this reasonably quickly, then there is another method. It's called decomposition method. And this is more reliable method, however it's a little bit longer. Well, let's see. First, we can try to use guessing method. I would suggest to go by guessing if one of those outside coefficients, either a or c, it's a prime number or 1. In the first example, the last coefficient is actually 1, so let's go by guessing method. To factor this polynomial, let's prepare two brackets. The first term in both brackets must contain x, obviously with some coefficient in front of x, so we're still searching for those numbers. Since the last number is negative, the product of those two free numbers p and q must be negative. That's why we use different signs. And also the product must be equal to 1, so the only choice is 1 and 1. Okay, therefore our search is narrowed down to just these two numbers, m and n. Since we know that the product of these two numbers is 10, there's only two choices, either 5 and 2 or 10 and 1. And we can try both of them. Obviously, these numbers, for example 5 and 2, could be written 5 here and 2 there, or the other way around. So we still have quite a few choices, like there's actually 4 of them. But maybe we can help ourselves by trying to obtain the middle term, the middle coefficient. It comes from multiplying the inner terms and the outer terms and adding them up. So since inner product is actually the same as this coefficient by x, and the outer product is actually the same as the coefficient by x in this bracket, and the two products are of different signs, so we know that these two products must actually differ by 3. Okay, therefore 5 and 2 would differ by 3. So if I place 5 here and 2 over there, let's check what will happen. The inner product is 5x, the outer product is negative 2x. So we are nearly there, but 5x minus 2x is actually positive 3x. We need negative 3x. So if this trial didn't work, let's change the places. So I'm going to erase the 5 and 2 and switch their places. Let's place 5 here and 2 over there. So products will be 2x, the inner product, and negative 5x, the outer product. Now it works. 2x minus 5x is negative 3x. That's what we needed. So this is a good factorization. Let's erase this part. That's our answer. As you see, the guessing method means that sometimes we may err and we may need to check a few cases before we actually get the right one. However, if those outside numbers are not too complicated, we don't have too many cases, and overall, the guessing method, especially if you are fluent with numbers, may lead you to a quick answer. Okay, let's try another example. First, let's arrange our polynomial in decreasing order of exponents, because otherwise our methods with signs may not work. So we must have our polynomial in decreasing order of exponents, and starting with a positive term. Okay, let's prepare two brackets. Since the outside terms are prime numbers, we shouldn't have too much trouble. So we must have a and a for sure. Since the last number is negative, so our product is negative, therefore we use different signs. Let's place plus and minus here. Now the 3 tells me that I can have 3 here and 1 there, or the other way around. The 2 tells me that I can have 2 here and 1 there, or the other way around. So I know my numbers, but I'm not sure which one to place where. So that's why I place them gently on the top. And now I'm going to look at the inner and outer products. The sum of those products must be negative 5, which means that one product must be a lot more negative than the other. So this times this should be a lot larger number. Oh, so maybe I should place the 2 over here and 1 over there, because this way I will be able to multiply 3 times 2, which is a lot larger number. So exchange them. I think this would work. 1 here, 2 there, and 1 here, that means I don't need to write, and 3 over there. Okay, so let's check. The inner product is 1a, so it's just a. The outer product is negative 6a. Negative 6a. So negative 6a plus 1a is negative 5a. Yes, the middle term agree. Therefore, this is the correct factorization. Now we can erase those extra markings, and we're done. As I mentioned before, the other method, which is more reliable but a little bit longer, is called decomposition method. So as soon as we have quadratic trinomial with composite A and composite C, we should use the decomposition method because the guessing method may take just too long. So the first step would be to state the outside product. In some textbooks, this product is to refer as master product. So what we do, we multiply the outside coefficients, 8 times negative 15, and I would suggest that instead of performing this multiplication, I would even factor. So I factor 8 into 2 times 2 times 2 and 15 into 3 times 5. Quite often when you see all the factors, it's easier to find the proper numbers to split the middle term into. We'll see this in a second. So we state the product, AC, and then we state the sum or difference, B, the B coefficient. Finally, we are looking for decomposition numbers. That means numbers that multiply to this product, and since the product is negative, differ by 2. Okay, so we can group those factors as follows. 2 and 5 together in one group, and then the other 2's and 3 in the other group. So we have 10 here and 12 over there. Now the larger number takes the middle sign. So the larger number is 12, should be positive. The smaller number is 10, so it will be negative. As soon as we've done this calculation, as soon as we have these two numbers, the rest is very mechanical. So these two numbers are not our final answers, not at all. These two numbers are the halfway answers. So what we do is split the middle term into our 12x and negative 10x. That's why we needed those numbers. It must be in such a way that the sum of those terms makes the middle term, that must be exactly the same, and also the product of those coefficients must give us the master product. We'll see in a second why. So we split this middle term using the found coefficients, obviously with x. We copy the outside terms as they are, and then we factor by grouping, group 2 by 2. So when we look at the first two terms, the common factor is 4x. Let's pull it out. What's left is 2x plus 3. And from the second pair of terms, we can pull 5 as a common factor with a minus because we want to start the bracket from positive. So if I pull negative 5 from here, what's left is 2x. And if I pull negative 5 from negative 15, what's left is plus 3. That's great. So now we have exactly the same factor, the whole bracket. Okay, let's factor it out. We take the 2x plus 3 as a common factor, and what's left is 4x minus 5. So that's the end. Notice that our decomposition numbers are really the coefficients of the inner and outer products. Here's another example. Since the leading coefficient is 3, we could try to factor it by guessing, but let's use decomposition again, just to practice this method more. Let's look at the master product, 3 times 20, which is 60, and the sum, 19. We can record this on the side. Product is 60, sum is 19. What are our numbers? Well, 15 and 4. 15 times 4 is 60, and 15 plus 4 is 19. So what we need to do is to decompose, split this 19x into 15x and 4x. Copy the outside terms as they are, no change here, and try to factor by grouping. So let's group the first two terms. Common factor is 3x. What's left is x plus 5. And group the last two terms. We can pull the common factor 4, and what's left is the same bracket x plus 5. Now, when we see the common bracket, we can pull it out as one factor, and the other factor is the remaining stuff, 3x plus 4. And it's done. Okay, try one more example. Again, my remark is use the guessing method if at least one of the outside coefficients is prime or 1. Use the decomposition method if both of the outside coefficients are composite. So in our case, the master product is 20 times 6, which is 120. The sum is negative 23. Since the product is positive and the sum is negative, we need to use the same signs. What kind of signs? Two negatives. So the two numbers that we are looking for will both be negative. Okay, to help ourselves to find these two numbers, I would suggest to factor 120. 120 is like 12 times 10. Let's find the prime factorization. So 12 is the same as 2 times 2 times 3, and 10 is the same as 2 times 5. When we see those factors, it may be easier to figure out how to group them to obtain the two numbers that will have desired properties. So for example, if I will group 3 and 5, making it 15, and the rest of it will make it 8, 15 and 8, well, they add up to 23, and obviously they multiply to 120 because all factors were exhausted. Okay, so we can use numbers negative 15 and negative 8. Well, that means we can split the middle term into negative 15 p squared q squared and negative 8 p squared q squared. Copy the outside terms and factor by grouping. So from the first two terms, we can pull 5p squared. What's left is 4p squared minus 3q squared. From the last two terms, we can pull negative 2q squared. Therefore, we'll get 4p squared. Switch the sign, so it's negative 3q squared. Fantastic, because it's exactly the same bracket. If it wouldn't be the same bracket, we wouldn't be able to factor, so we need to go back and check where's the possible mistake. Okay. So now we pull the common bracket, 4p squared minus 3q squared, and the remaining bracket is 5p squared minus 2q squared. And the question is done. Well, let's look at this example. This time we have something that is very similar to a quadratic trinomial, but has a plus b in a bracket. So I will suggest that we treat this a plus b as a new variable, as a new thing. This could be like a package. So the whole question is related to the regular 4x squared minus 19x minus 5 question. If we know how to factor this, we should be able to factor that. Notice that this x really represents this bracket. So how would we factor this one? Since one of the outside coefficients is prime, we could even try to guess. We have to have x and different signs, and those last two numbers must be 5 and 1. I still don't know if 5 is here or there. I need to try one or the other version. So if I put 5 here and 1 there, I'm still looking for those leading coefficients. Also, at the back of my head, I keep my eye on the middle term, which is negative 19x. How would I get negative 19x? That's a pretty large number comparing to 5 and 4. Okay, so the negative 19x must come from multiplying inner and outer products and adding them up. Since they are of different signs, the negative product, which is in this case outside one, must be a lot larger than the inner one. Okay, therefore I need to switch my 5 with 1 for sure. So it probably will work better if 5 will be here and 1 over there. Now the leading coefficients, well, they could be 2 and 2 or 4 and 1 or 1 and 4. So theoretically we have 3 cases, but practically I know that 5 times something must be at least 19 or higher, probably 20. So this number must be 4 and that one 1. Let's check if this distribution of numbers works. So the inner product is 1x, the outer product is negative 20x. Well, that's great. Negative 20x plus x is negative 19x. Okay, so this factorization works for that problem. Well, let's take advantage of it and use it in our problem. The only change will be that instead of x, we're going to write the bracket a plus b. So our two brackets will be 4 times x, but x is a plus b, plus 1, and then 1 times x, so just x, a plus b, minus 5. So now what's left to do is just open those inner brackets. Therefore we'll have 4a plus 4b plus 1 times a plus b minus 5. And it's done. Someone could say, I could square this binomial a plus b and open that bracket and then collect like terms and then finally try to factor again. Well, yes, you could, but if you do that, you may end up with expression that will be really hard to factor the way that we did here. Also, this is more elegant method and it works really nicely. Last example, let's try to apply similar strategy, except that, remember, the first step in any factoring is check for common factors. In this case, we have a common factor. It's actually 8. So let's pull the 8 outside of everything, and then we'll have x minus 3, which serves as a new variable, squared, minus 8 times this package x minus 3, and plus 16. Now I want you to think globally the same way as in the previous example. Replace this whole bracket by a new variable. Let's call it a. Then the related quadratic trinomial in terms of a will actually look like this: a squared minus 8a plus 16. And then you will see a lot easier that this is really a perfect square. It's a perfect square of a minus 4 squared, because we have a squared, then double the product, which is 8a, and then last term square, which is 16. Great, let's apply this in our problem. So we copy the 8, and whatever we have here is actually perfect square of a, but a is the whole bracket, x minus 3, minus 4. In the last step, let's just release this inner bracket. We'll have 8, and then it's x minus 3 and minus 4, so it's minus 7 squared. So we've got a really neat answer.